There is a number that haunts the corridors of modern physics, a specter that refuses to be exorcised by our most elegant equations. It is not a constant we have measured with pride, but a prediction we have failed with shame. That number is 10, followed by 120 zeros. To truly grasp the magnitude of this error, consider that the total number of atoms in the entire observable universe is estimated to be only 10 to the power of 80. We are not merely off by a decimal point or a factor of 2. We are wrong by a margin that exceeds the complexity of the cosmos itself. This is the vacuum catastrophe, also known as the cosmological constant problem, and it stands as the single worst theoretical prediction in the history of science. It suggests that according to our deepest understanding of the laws of nature, you should not be here. The stars, the galaxies, and the very fabric of space-time should not exist. The root of this impossible paradox lies in quantum field theory, the framework that describes the subatomic world with breathtaking precision. It teaches us that what we perceive as empty space is a lie. There is no such thing as a true void. Even in the deepest, coldest chasm between galaxies, the vacuum is alive. It is a bubbling, boiling cauldron of virtual particles, electrons and positrons, quarks and antiquarks, popping into existence for a fleeting fraction of a nanosecond before colliding and annihilating back into silence. This quantum foam is not a mathematical fiction. We have measured its effects in the lab. But here's the problem. Particles carry energy. And as Einstein revealed with his most famous equation, energy and mass are equivalent. Therefore, this invisible, frenetic activity of the vacuum must have weight. It must exert gravity. When physicists attempt to calculate the total energy density of this quantum vacuum, summing up the contributions of all these fleeting particles up to the Planck scale, the result is infinite. Even when we apply reasonable mathematical limits, the number remains colossal, a density so profound that a single cubic centimeter of empty space should contain more mass energy than the entire visible universe. If this theoretical prediction were true, the gravitational force of the vacuum would be so intense that it would have curled the cosmos into a microscopic black hole the instant it was born. Alternatively, if the pressure were negative, it would have ripped every atom in your body apart faster than the speed of light. Yet when we look out at the night sky, we see a universe that is expanding gently, driven by a dark energy that is incredibly weak, a ghost compared to the monster our equations predict. The discrepancy between the universe we see and the universe we calculate is that catastrophic factor of 10 to the 120. It is a screaming silence in the heart of physics, implying that either our understanding of the quantum world is fundamentally flawed or our concept of gravity is an illusion. Building on that spectral glitch, we must ask, how could we be so confident and yet so wrong? If the vacuum is truly this heavy, something must be canceling it out. For decades, the best minds in physics pinned their hopes on a beautiful, hidden symmetry. We called it supersymmetry, or SUSY. The theory proposed that for every particle we know, there exists a heavier, silent partner, a cosmic twin. For every fermion, a boson. These partners would contribute vacuum energy with the opposite mathematical sign, effectively subtracting the monstrous weight of the quantum foam and leaving us with a perfectly balanced zero. It was the perfect mathematical eraser, elegant and precise. But nature, it seems, is not obligated to be elegant. We built the Large Hadron Collider, the most complex machine in human history, to hunt for these supersymmetric partners. We smashed protons together at near-light speeds, peering into the subatomic debris for a glimpse of a selectron or a photino. We found the Higgs boson, verifying the final piece of the standard model, but of supersymmetry, nothing. The silence from the LHC has been deafening. The mathematical eraser does not seem to exist, and the vacuum energy remains uncancelled. This failure forces us into uncomfortable, even desperate territory.
We are pushed toward an explanation that many scientists despise because it feels like a surrender, the anthropic principle. If the math cannot naturally fix the error, perhaps the universe itself is the variable. String theory suggests that our cosmos might be just one bubble in a vast, frothing multiverse, containing perhaps 10 to the power of 500 different vacuums. In this landscape, the value of the vacuum energy varies randomly from one universe to the next. In almost all of them, the energy is indeed huge. Those universes collapse instantly or tear themselves apart before the first star can ignite. Life never starts. Observers never evolve. We find ourselves in this incredibly unlikely universe with its impossibly small cosmological constant, simply because it is the only kind of universe where we could exist. We are the winners of a cosmic lottery we didn't know we were playing, simply because the losers are all dead. But there is a third, stranger path. What if gravity isn't what we think it is? Recent advances in holographic theories suggest that gravity might not be a fundamental force at all, but an emergent phenomenon, a low-resolution projection of quantum data encoded on a distant boundary, much like a 3D hologram emerging from a 2D surface. If this is true, the error of 10 to the 120 isn't a mistake in calculation, but a mistake in perspective. We are trying to weigh the ink on a page and calling it a mountain. To solve the vacuum catastrophe, we may have to do the unthinkable, delete general relativity or quantum mechanics as we know them, and rewrite the laws of existence from scratch.